Hello everyone and welcome to this video presenting the latest developments in ANSA version 22. The enhancements on version 22 cover a wide range of areas and disciplines as well as generic pre-processing practices. Let's see them in detail one by one. We are going to start off with the graphics. By the improved utilization of the graphics card, we have achieved up to 2.8 times faster model handling in terms of graphics performance. When working on big models, user experience is also significantly enhanced during selection and hover highlight. And in relation to camera view adjustments, user performance has been promoted up to 80 times faster in terms of fitting view actions. In the field of modular run management, to offer a better overview of the changes in the life cycle of an entity, it is now possible to view the complete change-set history between two selected DM objects. A dedicated tab in the DM browser displays detailed information through a changelog and the listed change-sets actions. A graphical representation of all relations of a DM object is now available in the DM browser through the references graph that offers two modes, the where used and the life cycle relations. In the where used graph, the entities that use the selected DM object are displayed, including recursive relations organized per DM object type. In the life cycle graph, the pedigree of the selected DM object is displayed, which includes previous and next versions, references between ANSA files and solver representation files, as well as variant relations. We have also enhanced the management of model variants through the effective tracking of the relationship between multivariant and single variant subsystems. A lifecycle reference is created when a 100% variant is generated and saved in DM, starting from the 150% variant of the model. This can be seen both in the DM browser and in the lifecycle graph. The Smart Assembly process now supports the use of plain connection entities in connecting subsystems, and a new simplified user interface is introduced to facilitate and simplify the definition of intermodular connectors. A collective view of key results can be presented in the new results logbook available in the DM browser. The results logbook is a spreadsheet-like presentation of key value reports based on an Excel template that supports conditional formatting. The modular environment now supports the reuse of adapted base modules across simulation models and load cases. Transformed and renumber modules are now stored individually in DM to avoid duplication of adapted entities stored in DM, but also to reduce the build time. The default build process of the load case assistant is enhanced by including a new build action named as Apply Load Case Assistant. This action is used in load case headers to generate their FE representation before the output. Dedicated to crash applications, FMVSS 201U load cases can now be set up with the aid of target points load cases. Saving of the build setups in DM in a modular way is now supported to enable their reusability. In the DM browser, plain library items and folders can be directly imported through the new import function, while also direct editing of DM object attributes is now implemented. Last development in the modular environment area has to do with building of a new iteration of a simulation run directly in Meta or Combos through the respective function in the DM browser. This will launch a new ANSA process and load the simulation run. Continuing with geometry, In version 22.0, we enhanced the modify function by providing easy manipulation of cones and faces in a direct and interactive way, while in version 22.1, we further improved the function by adding more options. With regards to meshing, in ANSA version 22, we have totally redesigned the mesh module layout. The old mesh layout is now accessed via the classic mesh menu, while at the same time we introduce new mesh toolsets containing functionality targeted to each mesh type. Moreover, each new toolset layout has been redesigned as follows in the next slide. On the left, we see the old classic mesh layout, while on the right we see the new shell mesh toolset layout. Mesh improved functions are gathered under the new direct edit function. All functions for mesh generation are incorporated into two new buttons, mesh and reset, while other functions are reorganized into new groups to boost user productivity. In summary, we introduce 6 new different toolsets focused to each mesh type that can be shell mesh, middle, tetra, hexa, wrap, and voxel mesh. The new direct edit function is divided into 2 categories, elements and areas. For each mode, different options are available depending on the selected entity. In this animation, we see the elements handling using the new function that allows modifications on elements, on their edges and their nodes. In a similar manner, the direct edit areas function allows direct handling of macros, perimeters and hot points. The map block tool is another new feature of version 22.0 for Hexa mesh generation. The tool automatically detects and meshes mappable volumes, but also guides the user throughout the decomposition process from one volume to mappable subvolumes. In version 22.1, we improved the tool to be more robust, while also we implemented the automatic creation of initial and imprinted restrictions. Besides that, to enhance productivity during subvolumes creation, we added a new option to the cones projection function for automatic projection and pasting of red cones. With respect to batch mesh, we have greatly improved the algorithm for mesh creation around 2D holes, while for solid structural batch mesh, we added a new option for self-proximity mesh refinement in areas where quality criteria violation is expected. With respect to middle mesh, a new inspect tool is now available for easy identification of differences and deviations between middle mesh and 3D CAD geometry. When generating the middle mesh, a new option is added to inherit the middle mesh from a previous design version. The gray area is preserved from previous model, and only the green area from the new design is middle meshed. Moreover, a new tool to easily connect element edges to a given shell mesh is now available, while also we added new advanced tools for semi-automatic creation of middle mesh in special areas like grills and ribs. To enhance productivity when working on casting mesh, we added new options in the direct edit areas function, the stretch option, which is useful in regions with triple bounds to create planar macro areas, and the show faces option. Towards the same direction, we enhanced the middle mesh manual from side top function with more options. Continuing in casting, a new recover option is now available for recovering align constraints from the geometry. And fasteners library is now available inside the casting tool, allowing the fasteners recognition and mesh treatment, which can be directly applied from a DM library. With respect to features management, automatic identification of embedded clips is now feasible using a pre-trained ML predictor, while also mesh representation for recognized clips can be applied directly through the feature manager or through the casting tool. In order to populate the DM library with embedded clips, there is a dedicated function to isolate them and save their common representation utilizing an ML predictor. Their mesh representation can be also saved through a new dedicated plugin. Significant developments have been introduced in the assembly field. New FE representations for seam welds are added. A new hybrid weld shape of Y-joint and overlap allows to assign different specifications between the Y-joint and overlap parts. And a new FEMSITE shells on solids FE representation allows, among others, to create heat-affected zones along with mesh reconstruction on solids. The available weld subtypes are butt joint, overlap, and Y-joint. For the new FEMSITE shells on solids representation, welds IDs and contacts are defined through reference so that later modifications of referenced entities are automatically updated. Also, it is possible to parameterize the settings by typing expressions in specific fields. Moving to the disciplines and starting with durability. Pretension Assistant can now define bolt and bolt 4 as required in Nastran NX. The bolt direction can be defined either manually or automatically by the tool. Automatic detection of contacts between solid bolt and nearby parts is also possible, and a general entity builder of boundary condition is also created for further manipulation of the pretension. Automatic detection of node-to-surface contacts through Contact Assistant is now available. The detection is based on proximity, which is applicable on T-junction areas. Flipping of primary and secondary surfaces is available, as well as inspection of the contents of surfaces. Regarding the results mapper tool, integration points over thickness can now be used for mapping. The integration points option is available both for source and target location, and it is supported with the RBF interpolation method. Meta Results Mapping plugin is now able to map multiple states and assign them to the corresponding steps for Abacus deck by the respective interface option. In addition, the deformed geometry of the selected state can be used as source model to perform a more accurate results mapping. Through the same plugin, mapping of equivalent plastic strains is now supported. The equivalent plastic strain results in the metadatabase are recognized through specific labels, and after the mapping, appropriate solver entities are created for Abacus, Nastran, LS-DYNA, and Radios. New pretension representation in solid bolt connection is now available, which enables the automatic generation of pretension parametrically to the thread length of the solid bolt. This is followed by the definition of appropriate steps and loading conditions and is compliant with numerous solvers including Abacus, ANSYS, LS-DYNA, Nastran, and PalmCrush. Moreover, contacts through the solid bolt connection can now be automatically created between head and top part, between head and thread, and tight contact between thread and last part. This enhancement is available for Abacus, ANSYS, and Nastran. The function for calculating the interference closure has been enhanced. The function is applied on both shell-to-solid and solid-to-solid contact surfaces which are penetrated. The calculated value is equal to the maximum penetration between the surfaces. The complete general contact domain with all its options can be now defined in one card, the contact info card, available for Abacus contact pair and contact inclusion types, but also for marks contact. In addition, the contact definition for Mark Solver through the contact flanges tool becomes more intuitive and solver-oriented by providing new capabilities. First, the detection of whole contact bodies instead of sub-areas, and secondly, the automatic creation of all the necessary contact keywords. In version 22.0, a new FE2D cross-section solver has been added for calculating the cross-sectional properties of thin and solid sections. Moreover, in version 22.1, calculation of the cross-sectional properties of non-homogeneous solid cross-sections has been supported through the FE and FE2D cross-solvers. Calculation is available through CAT and multi-CAT functions and in the cross-module tool. Moving to the crash and safety discipline, the human body models family supported by the respective HBM tools is constantly expanding and enriched by the latest model version. Please note that the entire family of THUMS models is going to be soon supported. Regarding the FMVSS 201U tool, there are various new options, including the bleed-through option, which allows to quickly view the penetration area between the FMH and the trim. A limiting value is also available. It is possible to calculate the worst-case impact scenario by adjusting the priority between the divergence distance and the distance to hot parts. New local dx and dy limits can be used to define whether the final solution is acceptable or not. Auto-saving of the target point position is also possible when using the auto-positioning function. And the positioning process can be saved as a short animation. For vehicles having an active bonnet, the pedestrian marking can be performed on the deployed bonnet. The active bonnet is enabled from the Marking tab, which requires the definition of the hinge point and the pop-up distance. Moreover, the Euro NCAP version 9 protocol is now supported for defining the windscreen rear reference line and marking the zone between the WAD 2200 and 2100 lines with the bicyclist target points. In addition, the Korean NCAP 2022 proposal is now supported. Regarding airbags tools, a new passenger airbag modeling tool is now available for setting up an LS Dyna stitching simulation, while the existing airbag folding pre-simulation tool is enhanced to easily and quickly set up the folding tool's load case and preview their movement. A new barrier positioning plugin is available for positioning the barrier according to crash regulations, allowing for the parameterization of the protocol's default values. The reconstruct flange function is now available for sim welds. It acts as a pre-realization function, allowing, for example, the definition of a heat-affected zone only on the desired flange of the connection. The function is also available through the connection templates. The seatbelt tool now supports the effortless seatbelt passing through 3D slip rings such as D-rings and buckles. The low-speed impact tool now supports the US Part 581 standard for marking the vehicle and positioning the impactor in low-speed front and rear collisions. In the seat positioning tool, new protocols for frontal impact and side impact are now supported. In the instrument panel impact tool, a pull-down menu for selecting the positioning method is now added, and the tool is fully supported through its new scripting interface. Regarding impetus, a solver which was supported quite recently, new keywords are now supported, allowing the creation of a complete ready-to-run model. New keywords for isogeometric analysis are now supported according to LS Dyna version R13, such as keywords for the definition of IGA points, for the application of loads, and boundary prescribed motions, for the creation of tight contacts, and for the novel geometric definition by virtue of Bezier extraction. In addition, solid IGA elements can now be input, visualized, used in the model, and output. New functionality for IGA has been also introduced for morphing IGA shells through orthoboxes, for automatic creation of A and LC points on IGA holes, and for ensuring proper and acceptable by the solver IGA models through new checks. In regard to the kinetics area, a new plugin is available for running four-post analysis when working on vehicle models that include tires. The plugin places test rig plates under the tires and allows to specify a pattern of how the plates will oscillate, as well as the amplitude and excitation frequency. New integrators are now supported for dynamic simulations to provide a wider range of integrators, while also new formulations for smooth contacts, namely impact hysteresis and restitution, are now supported. A new type of force called modal force is now supported for applying time-varying distributed loads on specific regions of flexible bodies. Moreover, a new rubber seal forces plugin is available for the modeling of weather strips that are usually present in vehicle closures. Weather strips are modeled massively as a sequence of G-force entities along 3D curves. Proceeding with enhancements regarding the NVH discipline. In the NVH console, a new DOE study can now be performed on eigenvalues. The experiments are created based on different eigenvalues per component, providing the ability to conduct robustness studies for modal frequencies of various components. When calculating the fluid structure interaction, a new pressure equilibrium FSI algorithm has been introduced in version 22.0 for direct demix calculation inside ANZA and has been further improved in version 22.1 for more accurate calculation. Besides that, a new inspection tool is also added for assessing the quality of FSI calculated either by ANZA or any other external software. A new hydro-mount type of connector is available, which minimizes the complexity of FE modeling. The new connector type can be applied directly from ANZA connector entity or from within NVH console. In the NVH console, a new tool is now provided to prepare the model for gauge optimization and output ready-to-run a Nastran solver file for solution 200. The options for design variables are panels and thicknesses, and various options are available for the design objective. For example, the objective type calculation can be the SSQ, the average, and more. New features have been added to prepare a model for MNF creation. First, the ability to use RVDO instead of ASSET is now provided for handling the interface degrees of freedom. This means that the boundary condition for superelements calculation has changed, as now their interface degrees of freedom are unconstrained, while the constrained modes are replaced by residual vectors. Moreover, it is now possible to output the reduced display with plottles as well. Besides that, the display model tool is enhanced so that users can now select a target number for the nodes of the new display model, and the algorithm is improved for better feature capturing. Regarding CFD, in volume meshing, we have enhanced our tetrarapid algorithm so that it performs domain decomposition internally and meshes the volume using multiple cores. This can boost speed by around 3 times on large CFD volume meshes, and CFD meshes of billions of elements can now be generated and output. Size field functionality has been enriched by the ability to sweep size rules along predefined 3D curves. as example for wake refinement in cornering simulations. Moreover, a size field calculated from an external CFD solver can now be read in ANSA that will build a size field entity that replicates it. Regarding Hexablock tool, 2D boxes are now supported for generating structured 2D meshes, along with elliptic smoothing, available both for surface and volume mesh. Moreover, new functionality targeted for turbine applications can now automatically generate the Hexablock topology and apply meshing and smoothing. Native output of meshes for the solvers Raven CFD and Cobalt CFD is now supported. And when batch meshing tessellated STL data with the CFD mesh algorithm, the achieved quality is now very similar to the quality when meshing on plane geometry. In the composites field, with regards to the RVE generation in the homogenization tool, appropriate boundary conditions to apply periodic loading of the RVE are now generated, and a ready-to-run model is created for Epilisis, Nastran, Abacus, ANSYS, LS-DYNA implicit and PAMCrush implicit. Moreover, treatment of external RVE models from the homogenization tool is now also supported. A geometry file containing the RVE can be imported for meshing, the periodic boundary conditions can be created on the RVE, and the RVE can be solved directly with Epilisis for linear FE homogenization. Furthermore, already solved RVE models can be accessed by the tool, and the homogenized properties will be calculated based on the response of the model. Coupling of molding simulations for fiber reinforced plastics is now available in LS-DYNA through the Results Mapper tool. During the mapping of material orientation from Moldex 3D or Moldflow simulations, the tool can also create the keywords for the homogenization, depending on whether the homogenization is done in ANSA or it is performed during solution in LS-DYNA. New and enhanced functionality of injection molding is also introduced in version 22. The injection molding solver now works on mixed mesh as well. And regarding weld line nodes, users can now examine the specific angle values per nodes and visualize them through a fringe plot. Moreover, several enhancements have been implemented when conveying the effects of injection molding to FE analysis. Firstly, weld lines and orientation tensor results from molding analysis can be mapped. Prior to mapping, auto-matching of parts position can be applied if necessary. The mapped results are stored in the initial stress keyword of LS-DYNA for each element, and they can be visualized by creating a fringe plot. Using the file output LS-DYNA function, files ready to be used by CRAHFEM can be exported. On the electronic CAD, when reading electronic CAD data, the level of simplification can now be defined through 4 different options: the homogeneous board option, the homogeneous layers, the full 2D metallization, and the full 3D metallization option. Moreover, the eCAD Importer plugin now provides editing capabilities for StackUp and components. Since version 22.0, users can edit the layer thickness and can merge layers, while in version 22.1, users can also select the layers to be imported. In addition, since version 22.0, the component's thickness and standoff values can be modified as well. The automatic generation of batch meshing scenarios tailored to each level of modeling detail can be achieved from the batch meshing page of the plugin. The generated scenarios are filled with contents and are ready to run. Last, in the electronic CAD field, a new level of acceleration is now available at the 2D topology stage. The compared cases, as seen in the chart, which were two different models, each one with and without pins, have been accelerated up to 5.4 times compared to using the fastest algorithm of version 22.0. Moving to the morphing discipline and the optimization domain, new tools are available under new morph modules. Each tool provides many actions depending on the position of the mouse over an entity. The partition enables the creation of new morphs from existing ones. The adjust tool allows the shape adjustments. The move tool allows the movement of all structural entities of the morphs, that is, the morph points, edges and hatches. And the features tool allows features direct handling, like their relocation, copy or removal. Cross-section morphing is now quick and easy, and the 3D model can be morphed according to any modifications made on the cross-sections. User-defined cross-sections can now be selected to be preserved while morphing with form or DFM edge fit. The same functionality is available for the steady section constraint as well. The density of spot welds can now be respected when morphing is applied, but also it can be optimized by creating appropriate morphing parameters. Moreover, it is now possible to form the model with interactive handlers and extend, taper, twist, or bend it. It is possible to create beads and stamps that are detached from the underlying surface, allowing for specification of offset and flange width. Constraints can be created massively by selecting the entities or features to be constrained and creating one or more constraints in one step. Moreover, a new template is now available for OptiStruct optimization, guiding the user through the analysis setup. Through the bulkhead tool, new triangular and U-shaped bulkheads can be created. As far as optimization is concerned, response surface models can now be trained from completed DOE runs. The trained RSM can be used in the new Optimizer tab to start an optimization study. Experiments and optimization iterations can then be visualized through the respective interface. 3 new DOE algorithms are introduced for experiments generation for more efficient design space exploration. In addition, we introduce the simulated annealing algorithm to solve either RSM-based optimization studies exploiting the machine learning functionality or direct optimization studies based on direct connectivity with an FE solver. Last, in the morphing and optimization area, CATIA design parameters can now be imported and edited through the model browser. The active design parameters can be used as the source for the definition of ANSA design variables in the optimization tool. And then DOE and baseline execution can be combined with a predefined SPDRM workflow that will coordinate CATIA and ANSA calls to produce the requested experiments in the DOE setup. In the field of user productivity, the new hover highlight is focused on the model interpretation, enhanced 3D visualization, color entity type indication, and clear distinction of the hovered entity from its background result in intuitive geometric inspection. Entity details are dynamically displayed on screen through a label. Moreover, a new info function provides detailed information dynamically in graphics area upon mouse hovering, or printed in the ANSA info window upon clicking. The selection has also been improved, especially in areas of overlapping collinear entities. In this animation, we see a case of 4 overlapping entities that reference 2 coinciding nodes. The tab key is used to activate the text overlapping entity in a consecutive manner. By pressing on the indication of the total number of entities, we dive into information of connectivity and type of entities. And finally, there is a gateway to direct explode mode that allows precise selection. In version 22.0, the performance of penetration parametric check has been greatly improved, and various solver-related options have been supported. In version 22.1, a new option has been added to the fix function and can be used at areas where perpendicular flanges penetrate to obtain a smooth mesh result. The deck modules buttons have been reorganized and transferred under a new Analysis Tools menu, customized for each solver's functionalities and particularities. Organization relates to the basic steps and the tools needed for a structural analysis, as well as the discipline-specific and other special tools. The camera tool is now implemented in ANSA as well, and it not only provides information regarding the camera position, but it also allows for its advanced controlling. Direct element-based or area-based measurements can now be performed upon mouse hovering with a new dynamic selection mode. Higher order volume elements can now be input, visualized, used in the model and output. Last but not least, in the user productivity area, a new beta development environment is now available, which works with the Microsoft Visual Studio Code. The beta developed extension enables remote debugging of Python scripts that run in ANSA and Meta by using the debugger of Visual Studio Code. The ANSA virtual and augmented reality capabilities are further amplified. HoloLens 2 headset is now supported, and users can now participate in collaboration sessions in augmented reality along with virtual reality users. All types of curves are now available in the Curves menu of VR. Circles, arcs, and more can be created and modified both in VR and collaboration. Cylindrical morphs can now be morphed in VR and collaboration. The available options are to modify the outer and inner radia or to spin the circular morph edges. Sliding of morph control points is now possible in VR collaboration mode. The offline voice recognition is improved. Moreover, spelling and number dictation is now available along with a help tool. Real-time perception and interpretation of a scene with physical objects is now available in augmented reality. A significant enhancement in the drawing performance of custom avatars has been achieved in version 22.1, where the performance has been sped up 18 times. DOE experiments can now be selected and examined while in VR collaboration. And the sculpting tool is now available in VR collaboration, allowing to smooth or add material to topology results. Regarding the collaboration tool, it is now possible to use the sketch tool in collaboration from desktop users. Last, in the machine learning integration field, updates in machine learning in Convos version 22 include training and prediction of all scalar field primary and delivered results for all states. Training for key values, 2D or 3D results is now possible via a dedicated predictor train wizard. Key values, as well as all available 2D and 3D results recognized from the simulation runs results, are available for machine learning training. 2D plot results can also be used for machine learning training and prediction. Bending modes, vertical and lateral, can now be used for training and prediction with a feature-based type machine learning. Along with the first torsional mode, the ANSA wizard, which now requires 6 load case points, will now create key values for bending lateral and bending vertical if they are identified and can be trained. Moreover, feature-based training is now open to be used for any type of response. A similar wizard is also available in version 22.1 to identify local modes and use them as key values for machine learning training. Prediction is done in combos for all modes, that is, the first torsional, first vertical bending, and first lateral bending at the same time. And with this we conclude this presentation. Thank you for watching.